Hello everyone. In this problem, we will discuss five transistor OTA structure. That is a part of CTQ. There is a different series for a five transistor OTA also. But in this particular question, the input pair is my PMOS and the current mirror is the NMOS. So, especially I designed this question for the frequency analysis of the five transistor OTA. Rest all other analysis can also be done, like noise analysis, mismatch between the input devices. So the offset analysis can also be done. But I am not doing these things here because already they are provided in the five transistor OTA series. You can see there how to calculate the noise and mismatch analysis from there. Okay. So in this video, the target is to find the transfer function. So how to calculate the poles, zeros, and how to write the transfer function. These are the only few things that I am considering here. Okay. So first of all, we will see the exact question analysis, and after that, what extra that I can discuss about this, we will see. Okay. So what are the possible pole locations? So first thing that I will like here, what are the pole locations? Okay, so pole locations, we have to see the nodes where there is a possibility of capacitor, there can be a node or there can be a pole. And what about the condition of zero? So any node consisting capacitors, any node having capacitor, a node having capacitor, so there is a pole. So there is a pole. Okay. So I have this node that I call output node, this node which I call node X. This is also the same node, so it can be called as the mirror node. There is one this node. Okay, so these are few nodes. So because this current source on the top is nothing but also a M not transistor, which is also PMOS. So there will also be pole included there. So what we can see, we have to look for the capacitance at that particular node and the impedance looking at that node. So what are the possibilities? The first node, let I say output node. So pole at output node. So the first is pole at output node. So what is there? Capacitance at this node is what CL plus other capacitance which are C drain to source means yeah. C drain to source or drain to body, but right should write drain to body, or simply I should say they are drain capacitors. Okay, so drain to body capacitor of transistor 2 plus CD drain to body capacitor of transistor 4, and any other possible capacitors that can be there. Capacitor drain to gate for 2 plus capacitor drain to gate for 4. So these are few possible capacitors. But we can see the CL is too large because it is external load. It is of order of picofarads. So it is the order of few picofarads. Let I say there's a 1 picofarad, 2 picofarads, and these are very small caps. These are small caps. So overall, the output cap is what? Output node cap is equal to CL. Okay, so this will give me the one pole frequency. What is the output impedance at this node? So output node impedance is what? Output node impedance. I am directly writing, not going exactly inside this expressions for the output impedance calculation, but directly everyone can see for this particular node what is the impedance. This is the drain to source resistor of M4, drain to source resistor of M2. Okay, so I will say RDS2 parallel RDS4. So this is looking at impedance at the node output. I will say this R out, then R out is this. So what is the pole frequency associated with this pole? That is omega p. One is what? 1 upon R out CL. It is giving me 1 upon RDS2 parallel RDS 4 into CL. So as you can see, this means CL is the external capacitor. So this term is small. So omega p is small because of external capacitor because of external capacitor cap CL. So what is contributing to this CL? Why this is large so that your omega p1 is small? I will say this is omega p1. It will later act like a dominant pole frequency. But why this is large? Because we can see for this for the 5 transistor OTA structure, this is my first stage. This is my GM stage due to this 5 transistor OTA. This is V1, V2. So this thing is what they see out of this stage, and the further stages, which are the second stages and other stages, or I can say second stage, or I can say load stage, second stage, whatever we can call this, because the output of this first stage is going to feed the input of these further stages. So there only the input capacitance C into will contribute to this CL. So CL is some load capacitance or output capacitance that we used for this particular first stage, or we are just modeling using the load capacitor, but it is nothing but a capacitance input capacitance of the other stages. So it is already large capacitor. I am modeling it as a CL. Okay, so this is contributing to my dominant pole frequency, or which I call R out CL, R out of stage. So what are the other possible pole locations that you see here? So in this other pole locations are X and node. What I call this node? This node I call Y. Okay. So other pole locations are node X and Y. So what we can see. So what is there? Sorry. So this is my CL that we have seen. This is a first or can say dominant pole is contributed by this. So this node is what? Means actually there is a M naught transistor which is biased at some BB naught. It is my BDD. So it is also contributing to some pole, and this particular node is also contributing to the pole. Okay. So it is like this. Okay. So what is the node X capacitance and node Y capacitance? So we can see the cap at node Y is what I will say cap at node Y. So it is what this capacitor that I will say drain to body capacitor of transistor M naught, and other possible caps are what you can see. So these capacitors are somewhat like C drain to source of or drain to body of M naught, that I will say this, and other are source to means this body capacitor for these transistors M1 and M2, but these all are like a small capacitances. So I will call this is a small value, small cap. Okay. Now other is contributing with this. So what we can see, this X node is looking what? The upside capacitance, downside capacitance, and gate capacitance of both of M3 and M4. So it is actually looking some higher capacitances. What is cap at node X? It is looking for CD of M1 or CDB of M1 plus CGB gate to body of or gate capacitor of 1 plus gate capacitor of CB of 2. Okay, so this node X is seeing much higher capacitances that you can see because the gate capacitance is always higher because of in means oxide there. So because of oxide there, this is a higher capacitance. It is higher than cap Y. Okay, because of it is a gate capacitance. It is mainly contributed by gate capacitance of M3 and M4. So some of you can see this node bicapacitance can be treated as a pole, but yeah, obviously it will contribute to the pole, but this pole is far apart because this is only dependent on the few parasitics. But the node X, especially depending on the gate capacitance, and gate capacitance is higher than the other capacitances. You will see because directly the gate area is multiplied there with the WL. So for any size of this input pair, usually we keep the input pair of means this what I call the mirror devices. They will contribute means due to this mirroring structure, this capacitor has the effect of gate capacitances, and gate capacitance is higher than the other. So it can be higher than this cap at node Y. So, but there is also zero contribution. So first we see that what is the means second pole, the second non-dominant poles, or I can say if I call it second pole is nothing but C at X and what I say R at X. And what is the third pole, which is 1 upon C at Y and R at Y. But it is insignificant or it is very far because here capacitance is also low, and also that I can say R out is means GM. So this pole will be something like GM of 1 2 nearly divided by C at node by. And what about this node? This node cap is something the higher cap that I will say CX. And what about this means register there? Register is here also high. So what is the value of the register here? It is nothing but yeah. So I can say 1 upon GM of 3 4. That is not that high, but you can see due to this value of CX, these poles are actually comparable. If I consider the GM nearly equal, so what we can see omega P1 is what 1 upon R out CL, it is a dominant pole. What is omega P2? It is 1 upon CX RX, which is nothing but GM of 3 4 by CX. And what is omega P3? It is GM of 1 2 by C by. So CX is higher, that's why it is non-dominant pole. Non-dominant, or I'll say first non-dominant pole. This is called as second non-dominant pole. Second non-dominant pole. And this is our dominant pole. Okay, so with this we have seen the pole calculation. Now we will see the zero calculation. So zero calculation is a bit tricky. For that we will follow a particular method. So okay, so this is my input pair. This is my input pair. It is I should call it RDS of a transistor, PDS. Oh, sorry, BDD. So what we can see is see how to calculate the Miller pole. Oh, sorry, Miller zero. Mirror zero, not a Miller. Okay. So I'll consider here one cap which is called the CX. This node has CX cap. So the output has two paths actually. When we are looking for zero, what in general how do we calculate a zero? In general, how we calculate a zero? Actually, I should first focus on that. So any transfer function is what? V out of S divided by V in of S, or I would say numerator of transfer function divided by denominator of transfer function. So for pole our Vn should 0, so that or I can say V out can be infinite, or overall I can say this transfer function is infinite. For 0, for 0 transfer function is 0. In turn I can say my V out is 0 for non-zero Vn. I can say like this, we can analyze. So what I want to see, make the output 0. So first we will make the output short so that V out is 0. And I'll calculate the two currents which are contributing to this path, because if output is 0, what we can say, this is what R out times your I short circuit is equal to 0. This is only your output voltage. So R out is something non-zero term, so I can see my ISC is 0. So when there are two possible paths, because we can see any perturbation on the inputs, there are two paths. One path is this. This is due to this GM del VD of this transistor, and there is a one path. This is GM del VD of this transistor. So how we will calculate it? Let's say this is virtual short. Okay. So what can be analyzed here? You can see if there is a like del V perturbation up, and here is a minus del V perturbation, and what we will see actually, this is a virtual short, so it is my virtual short. So what current will be generated here? So yeah, so this thing I'll okay tell on the next page how correctly we can see this. Okay, so this is the structure. Okay, virtual short. Okay, so what kind of analysis I want to do here? I'll show the direction exactly. Otherwise, many people are confused here. This I call CX. I want to see the output short circuit current to be 0, because for the finding the zero calculation, because we are doing the zero calculation. So for the zero calculation, your V out should be 0, hence or ISC should be 0. So from where ISC is coming? One this direction is there, other this direction is there. So overall I can say ISC is nothing but I down plus I up. There are two branches. So there is a possibility of making it 0. One branch is the current is coming from upside because of this transistor of input pair, and other is coming from lower side because of this transistor of input pair, which is generating the current, and this current is copying by this current mirror, so it is coming from here. You will see this thing more clearly here, how it is happening. The direction matters a lot. For the PMOS, if there is any positive perturbation of this node and this node is 0, then there is a current generation that I call, always in any transistor, the current generation is only GM VGS, and direction is drain to source. Here is also, I will say, okay, I'll remove it. Here also the direction is, I should remove these things. Okay. Here is also, if here is a minus del B perturbation, I will say this is also GMVGS. So we will see exactly what is happening. Here the source is ground and there is a del V. So I can say the direction of current in this is GM del V. Okay. What is the direction in this? Actually, what is here? Gate is minus B and source is 0. So what is GMVGS? It is nothing but GMBGS. So this. So what exactly we can see? Actually, the upper current is coming down because of minus direction. So we can see from here, this structure is there. Here is a mirror. I am not drawing the mirror again. Here is my mirror. Okay. So what is happening here? This is the current that is coming this side. It is GM del B, Also in this branch there is a current which is coming down, which is gm del b. So this current is going to output. Okay. So one more thing that is missing here, I will tell later, because this is an exact analysis when effect of Cx is not considered. So from this, what we can see, okay, this direction is upper side. What I am not considering here, later I will consider in the analysis. Okay, so here I am not considering the effect of Cx here. So what I am seeing, the Cx, if the Cx is not here, what we can see, the total current is here like Gm del B. So what is the short circuit current? That is a 2 Gm del B. Can it be zero? No. So if there is a no cap, significant cap is not here, if I am not considering any cap, then we cannot say there is a zero, because this cap is making contribution to input to output direct relation, because there is a mirroring action happening. Due to the mirroring action, there are two paths for the current, so that hence total current can be zero. So now consider the effect of Cs. Now we consider the effect of Cs. Okay. Now consider the effect of Cx capacitance. Okay. So here is my Cx. Now what we are seeing, that what the thing I was not considering here in that previous diagram, actually the current generated by this device is what, Gm del B. This device is also generating the current in this direction, Gm del B. Okay. So I have to find a short circuit current. Before that I should change this. This is my zero. Okay. This is my ISC equal to zero. I have to make this my target. So what we can see here. Yeah. So at this node, what we are saying, actually there's a, let I consider this node potential is Vx. So this current which is coming Gm del B from the transistor M1, it is splitting into the two parts. So this current is splitting into the two halves. So one current is going this way, other current is going this way. No current in gate, so it is directly going down. So what is this? Actually, this current is what? This is simply because this VGS is what? Vx. So it is Gm of 1 into Vx. Okay. Sorry, not Gm of 1. It is a third device. I am just confusing in it. So let me clear. So what we are seeing here, one current is this way, one current is this. What is this current? This current is my Gm3 Vx. What is this current? This current is nothing but Vx Cxs. Okay, so these are the two currents. So what can be written? So actually again the same thing that we are missing here, the direction of this current. It is actually going up, on the smaller scale. It is going this way. Okay. What are these two currents? I will write from the node equation at Vx. Node equation at Vx. What we can see, Gm del V is equal to minus of Gm1, Gm3 Vx plus Cxs Vs. So this way I can write it minus of Gm3 plus Csx into Vx. This is my Gm1 del B. Okay. So which current is actually copying here? See this that I say Gm3 Vx is copying here. So overall what I will write here, Gm del B minus Gm3 Vx. So Gm del B minus this is my ISC. This is the node equation at output. Node equation at output node. Okay. Gm del which is coming from top side minus Gm3 Vx, because whatever the current is there in this device 3 is only copying here. So Gm3 Vx. So minus Gm3 Vx equal to ISC. This is equal to 0. So what can be said here? GM del B equal to this is GM1, GM1 again. It is GM1, GM1 because 1 and 2 are same. Okay, so GM1 del B equal to GM3 Vx. So what can be written here? It can be written like, so if this is equation 1, this is equation 2, I can put GM1 del B in the equation 1. So what can be written as then equation from equations 1 and 2, from equations 1 and 2, gm3 vx equal to minus gm3 vx minus cx s vx. So if vx is cancelled, what we can see here, cx s equal to minus 2 gm. So S, or I can say omega Z, here is what? Minus 2 gm by Cx magnitude. Okay. So this is actually location of 0. Zero's location. The node Cx can provide a 0. So now we can see, we can revisit the calculation. So the 0 is coming at omega Z is what? 2 gm 3 comma 4 divided by Cx. And what is the pole at x? This is 0 at x. What is the pole at x? It is gm 3 comma 4 by cx. So from here we can conclude 0 0 is at twice frequency that of. Okay, okay, so what we can see, okay, yeah, so what is omega g at x, which is 2 gm 3 4 by cx. And what we have seen, omega p at x, which was first non-dominant pole, it is gm 3 4 by cf. So what we can see, 0 is at twice frequency. Okay, 0 frequency is twice of that pole frequency. So what we can see from here, now we can write the transfer function. Transfer function s, or I will say h of s, that is nothing but b out y b in of s. So the DC gain, that is nothing but GM of input pair, and RD2 parallel RDS4. So the for 0 is 1 plus SY omega ZX, 1 plus SY omega P1, 1 plus SY omega P2, 1 plus SY omega P3. So actually there are possible poles. These are the possible poles, but actually we see that this is a first order system. We can approximate it because this term is non-significant, because this pole P3 is very far. This pole P2 is also far, that I call it as GM34 by CX, and this zero frequency is 2 GM34 by CX. So in general consideration, this is the complete transfer function, that this is the complete transfer function. What is this? This is nothing but GM of input pair 1 2 times RDS of 2 parallel RDS of 4. This is complete expression. But in general, this system can be approximated as the first order system, first order approximation. Because in comparison of CL, these caps are not contributing to the much. So it can be written as A naught y 1 plus SY omega P1. It can be approximated like this. Okay, so exact analysis we have seen how to calculate the zero, and how to means calculate the poles. So that thing was the motivation of this video, because the mirror pole is important here. And the calculation of mirror pole is also very important. So now this homework for you remains. Now analyze some big structure and calculate the zero. I want to the zero calculation for this structure. Yeah. So this calculation is a bit lengthy, but you have to calculate what is zero location. Okay. This is my telescopic structure that I'm drawing, and I want mirror pole here. So this is the homework for this particular CTQ. Okay, this is the output. Out, of course, load is CL. So calculate the poles and tell about the dominant poles. Okay, so this is my. Uh, Sorry, I think this is a mistake that I have done here. Yeah. So here we have this diode connected device and this diode connected device. Okay. So you have to find what is the homework. Actually, you have to find pole locations. Find zero location also and zero locations. How many poles and zeros are there? Okay. And third thing is that dominant pole, first non-dominant pole, first non-dominant pole, and other non-dominant poles. The non-dominant pole. You have to analyze in the way because I want minimum dominant pole, first non-dominant pole, also second non-dominant pole. How will you analyze? I want to see. Okay. So this is, I think, enough for this video. Once I recap it. Okay, don't worry for the biasing of the circuit. If someone might be thinking of the biasing, this is actually taking the biasing from outside. This is means biased now because of the current diode connected devices. So this point that I call BB of 3 4, it is biased from outside. Okay, this is the external biasing. External biasing. So my point is not here biasing. My point is frequency analysis. Okay. So what is the recap of this video? I'll go. So actually we proceeded in the way the question was to calculate the transfer function, the frequency analysis, common mode ranges, so and closed loop stability. Okay. So still the common mode ranges and closed loop stability remained for this. That I will complete very soon. Okay. So what is closed loop stability here? So that I already told you, closed loop stability. So once we have a transfer function, suppose the open loop transfer function we have a of s directly, which is nothing but a naught 1 plus sy omega p1. Okay, so this is the first order approximation for this transistor. First order approximation. Even if you want to include the zeros also you can do. Then for the closed loop transfer function we can directly go for this as, consider some beta 1 plus beta as, where my beta is, let's say, half or whatever the factor due to the resistor divider. From here we can see closed loop stability of the first order system we have seen in the previous CTQ problem also. If my open loop transfer characteristics, sorry, open loop body plot is like that, then what we can see for the closed loop, it is somewhat here. Its gain is reduced by the factor of 1 plus a beta. Its bandwidth is increased, but UGB is same. Okay, so it's this is my 3 dB of closed loop. This is the omega 3 dB of open loop. Okay, this is the gain of open loop. This is the gain of closed loop. 1 plus beta a naught. Okay, so from here what we can understand, Actually, all the things are analyzed already in the previous video, so I am not taking into the much depth. So what to say of the swing calculation that I'll also take faster. For its this is the magnitude plot. For its phase plot, you can see the previous. This is the magnitude plot. For the phase plot, you can see previous CTQ. CTQ 6 you can see. Okay, so for the swing calculation, directly you'll see here. This is my M naught. So this is the common mode calculation of 5 transistor OTA. Okay, so what you can see here, yeah, yeah, this is the common mode voltage. So what is the output? Swing of the output I have to calculate. Anyway, you can calculate the anything. So if this node is going up, what is the possibility for particular amount of current 2 I naught? This VSG is fixed. So when this VCM is going up, this node is going up. So this transistor M naught can be crunched. So we have to keep this in the saturation. So what maximum value of this node Vx can go? It is nothing but VDD minus VD set of the M naught transistor. Okay, so what max this can go? VGS of this, VGS of 2 plus Vx, it can go max. What it can go down? When it will go down, this transistor, transistor M2, this is one, this is 2. When the common mode, also the common mode is applied here. So when this common mode will go down, this transistor M2 can go into the out of the saturation. So what is the reason for that? You have to find out. And what will happen at the output? Output we can see what maximum value the output can take simply the overdrive of second transistor plus overdrive of M naught transistor. So it can take the maximum value of VDD minus two overdrives. So okay, I will say it can take maximum of VDD minus two overdrives. It is the overdrive of second across the second transistor and overdrive of M naught transistor. Okay, so what minimum it can go? It can go minimum of one overdrive, that is of this transistor. This is the overdrive of 3. The minimum it can go overdrive of 3. The overdrive of 1, 0 and 2 I considered equal, so I am writing 2 overdrive. So this is the output swing. You can see this analysis. See this analysis in 5 transistor OTS series that is already running parallel to this CTQ series. You can see this common mode analysis in great detail. Okay, so this is enough for this video. Later in coming CTQ's session, we will see what possibly I can cover. So I'm also getting the request from the people about the switch capacitor circuits, especially with the op-amp, because these are also these some hot topics I can say for the interview. Last year, to the many people, I think many people, many of my friends got this question of switch capacitors. So what they are doing simply is sample and hold time analysis of switch capacitor circuit with op amp. So there are good, really good questions are there. I will take these in the coming CTQs. People are asking for that. And also, apart from that, the maximum things that I'm covering is around this transistor section that up to the 5 transistor OTM maximum I'm going. I'll go to, after the switch capacitor circuit, I will switch to few good RC questions also that were asked in the recent years, or the possibly that kind of questions can be asked. So the most probably this series is going to be very interesting. So if you have any doubt in particular structure of 5 transistor OT, then follow the other series which is running already, 5 transistor OT series. Because I cannot tell everything in detail here, because this is the only point that I covered here was most maximum time I have given to this frequency analysis of this circuit, and after that little about the output swing. So in detail analysis, you can see in the 5 transistor OTS series, and also the noise and offset analysis of this particular structure you can see in detail. That I cannot cover here because of video length will go more than 2 hours. So I think this is enough for this video. Thank you.